Hey, so let's take a look at significant figures. These are numbers that are significant. I mean, important. I mean, yes. Anyway, so we've been looking at measurements and how we start to carry through when we measure something the correct units, that we know what we measure and how we measured it. Significant figures take it a little step further and how we start to tell the precision of the measurement. So just the what of significant figures is referring to the precision of our measurement. So when we say significant figures, what we're talking about is how many numbers in our measurements we know to be important or were measured. So numbers are reported in measurement and they are limited by the tool that we use to measure. Significant figures in our measurement include all of the numbers we read plus our degree of uncertainty. And so the real good analogy I can give you is a graduated cylinder versus a beaker. Well, one of them is much more precise. If I were to read the volume of the green liquid in this one, I would get 40 mils. I only have a line for 50. So the second I estimate a volume, boop, I'm done. 40 mils. If I were to put it into my graduated cylinder, because I have more calibration, I get to report more digits. So now I can say that it's 25.2. 25.2 has way more numbers than 40. Our graduated cylinder has more precision and more significant figures than our beaker. And the reason we care is because this affects then anything we do with those numbers. The kind of old adage, the saying, your chain is only as strong as its weakest link. The same is true for our measurements. Anything we do, we can only be as precise as our least precise measurement. And our significant figures keep us true to our measurements. It's our bookkeeping method to make sure we're matching the precision of our tools. And so moving forward, we're always going to be looking at our sig figs. Well, how much precision did we measure? We have to match that then in our final calculation or our final answer. That's really where we're heading when we start to look at our significant figures. But first, we need to figure out, how do we actually go about finding the number of significant figures? And there's two types of numbers. The first type of number is if there is a decimal present. If you have a decimal present in your number anywhere, you're going to count from left to right, starting with the first non-zero digit and counting everything after. So for example, in this first number, 38.15, we're going to count from left to right. Our first non-zero number is the 3. That was significant. It was measured. So was the 8, so was the 1, so was the 5. This has 4 significant figures. In our second one here, again, decimal, count left to right, it has 2 significant figures. The third one here, 6, 5, and 6 are all significant. This would be 3 significant figures. The last one would have 5 significant figures. Where this becomes tricky is if there's zeros involved. And so if there was a zero out in front, you wouldn't count it. See if I got some examples here. Throw some on the board. If you had 0.0001 gram, 0.0001 gram, these zeros out in front are what we call placeholder zeros. Decimals present, we're going to count left to right. Our first non-zero number is the 1. This has 1 significant figure, 1 sig figs. 1 sig figs. We can rewrite this. This is a little number. This is 1 times 10 to the -4th gram. This still only has 1 significant figure. These zeros out in front, they're sometimes called leading zeros. These zeros are placeholders. If they were after the decimal point, if they were what we call trailing zeros, we would count them. If our mass came out to be exactly 21.0 grams, left to right, we start with the 2, we count everything after. This would have 3 significant figures. This 0 tells us that whatever we measured all the way to the 10th place, and it was right on the line. And so that's where, when we start to look at our zeros, how we keep track of, is it significant? Is it not? If there's no decimal present, kind of rule number 2, if there's no decimal present, you're going to count from right to left. Again, starting with your first non-zero digit and counting everything that comes after it. So for example, this first one here, we would count right to left. We'd start with the 5 and the 2. This has 2 significant figures because, again, we can rewrite that number. It would get rewritten in scientific notation as 2 marker, come on, marker. As 2.5 times 10 to the 4th. And this was inches. Again, still having just two significant figures. All of these zeros are, these trailing zeros here are placeholders. But the one below it, we got this decimal. So we count right to left. We'd start with the 2, count everything after it. That is exactly 3 significant figures. Our third example here, we'd count right to left. That has 1, 2, 3 sig figs. Our last value, we'd count right to left again. We'd start with the 5, count everything after it as well. 1, 2, 3, 4, 5 significant figures for the last one here. So that's how we go about determining, when we just got a number, how precise that number is. How many sig figs does it have? We just go ahead and we count them. And this tells us then how precise we get to be in our answer, because oftentimes we're going to do math with these measurements. And so when you start to calculate, your final answer cannot be more precise than the tool you use to measure stuff. You don't get to make up precision, not allowed. A calculated answer must match your least precise measurement. There's kind of 2 types of math operations. We're either going to add or subtract, or we're going to multiply and divide. If you're adding or subtracting, you're going to do the math like normal, and then you're going to round your answer to match the measurement with the fewest decimal places. So for example, if we add these 2 values together, we don't actually know what's in the hundredths place for this first value. We're assuming it's a 0, but it might not be. We don't know because we didn't measure to that place. So because of that, we're going to have to round our final answer to match our least precise decimal place. So we round it to the 10th place, 1 decimal place. 4 or below, let it go. 5 or above, give a shove. Because the next number was a 4, it drops off of our calculation. If for some reason your number was a big number, a whole number, it's like, I don't know, 1,032 grams, and you wanted to round it to 3 sig figs, well, you still need something for the 2, but you don't want to count for sig figs. So it becomes a 0. You wouldn't round 1,000 to 103. You still got to put that 0 in there to keep a placeholder if you're rounding your answer to match your decimal places. Cool. So adding or subtracting, we're going to look at decimal places. If you are multiplying or dividing, you're going to round your answer to have the fewest sig figs. So decimal places, adding, subtracting, the fewest number of significant figures for multiplying or dividing. So for example, if we took 2.4, meters times 3.1145 meters. I'm grabbing my calculator real quick. I'm making it up. So we do the math just like normal. 2.4 times 3.115. We get an answer of 7.476 meters times meters is meters squared. We're less worried about the units right now. We're going to layer that in a little bit later. We're more worried about the precision here because I got 2 numbers. I got an answer, but this answer can't be more precise than our least precise measurement. Our first measurement here had only 2 sig figs. Our second measurement had 4 sig figs. Because we only had 2 sig figs for this value, we're gonna have to round it to be 2 significant figures here. Excuse me. Next number is a 7. That's gonna round us up to 7.5 meters squared. And this is where our significant figures are really, really important. This number can't be more precise than our least precise measurement. That's really why we have these significant figures. Cool. Armed with that, hopefully you're able to navigate these problems a little more succinctly. If you got questions, feel free to reach out.